Welcome to the fourth lecture of week 8. If you remember, we've been doing mutation testing throughout this week. Last lecture, I took an example of a small program. We did two methods, and I told you how to apply mutation to particular statements in the program, how to write test cases that would kill those mutants. We distinguished between two notions of killing, strong killing and weak killing. We saw examples of both kind. We also saw examples of an equivalent mutant for the first method that we saw. How are these mutation operators obtained? How are these statements mutated? These statements are mutated by using an underlying set of mutation operators that are available for several different programming languages. So the focus of this course is to understand mutation operators. As I have been telling you, mutation operators are available for many programming languages like C, Java, Ada, Fortran, Lisp, and so on. They are available for integration testing of C, which focuses purely on procedures calling each other. They are available for integration testing of Java, which focuses on class integration testing, methods calling each other, and so on, which we will also see. When it comes to specification, mutation operators are available for formal specification in modeling languages like SMV and USMV. They are available for markup languages like XML, which we will see as a part of this course. Each of these languages we know is different, forms a slightly different subset, has different syntax, and more or less the same set of programs can be written with any programming language. So what we will see today is like a common set or a generic set of mutation operator that cuts across all the different programming languages, and we will also see mutation operators that apply at the individual statement level within a program. So these are not the operators that are going to focus on integration testing, as I told you here. They are going to focus on unit testing. We are going to mutate individual statements in the program by making small changes to each statement in a program as and when it's necessary to test the execution of a program. What are these mutation operators designed for? Typically, programmers, when they unit test their code, why do they do unit test? Unit testing helps them to detect simple mistakes that these programmers make themselves. For example, instead of writing less than or equal to, they could have written less than. Instead of writing array indexes beginning from 0, they could have written as array indexes beginning from 1, and so on. So these are simple programmer mistakes. And what we are going to see is a reasonably exhaustive list of mutation operators that try to mimic or mutate to mimic these simple programmer mistakes. These could be operators that change relational operators. As I told you, maybe he's supposed to do less than or equal to, but instead the programmer did less than. Or maybe greater than or equal to, instead he did greater than. Or maybe he had to do I++, instead of that he did J++. So that means a changed variable name or a variable reference. So we are going to see mutation operators that mimic these kind of mistakes. They make small changes that mimic these mistakes and see how the program behaves, if the mutant can be killed or not. They are also designed to encourage testers to follow common testing heuristics. What do we mean by that? One common testing heuristic which every individual tester is supposed to do is to see how the individual method that he or she has written, when the variables in that method become 0, is it fine? Because maybe somewhere in the code there is a division by 0, or there's division by some number that could potentially become 0. So every programmer, the onus is on each programmer to test their code to see if all exceptions, including variable names being 0, are being handled correctly. So for that, we'll see a specific mutation operator, which we already used in the last lecture, called fail on 0. Mutation operators that we will see will be fairly exhaustive, in the sense that it will be like a laundry list of all possible different mutations that you can do to a particular statement. Typically, most of the times, it is not the case that a programmer has to use each of the kind of mutation operators that we will be presenting today to be able to test his or her code. But as a list, the onus is on these tools and on us to be able to provide an exhaustive list. We never know which of these operators from the list is going to be useful to a programmer for his or her code. But this list is exhaustive. But the use is not meant to be exhaustive. Use is meant to be selective as and when needed for specific pieces of code for unit testing. And while mutating a program and testing it, the programmer has to create tests to be able to kill the mutants, either strongly kill it or weakly kill it. So when it's in this exhaustive list of mutation operators, how will a tester pick which are effective mutation operators? How do I know which set of operators are effective? So here is a definition of effective mutation operators. It says, if tests are created specifically, let's say you start with a collection of mutation operator, call that set as the set O, given as O1, O2, O3 and so on, some finite set of mutation operators. You've made these mutations one at a time to the given piece of program, and you're writing test cases to kill these mutation operators. If the test cases that you have written to kill these mutation operators also happen to kill other unused mutation, the remaining mutation operators with very high probability. You may or may not know whether they've actually killed, but let's say they happen to kill the other remaining mutation operators with very high probability, then you say that the underlying set of mutation operators that a programmer has picked is turning out to be effective. So just to repeat it, a programmer has a method with him, and now the idea is to apply some set of mutation operators to test that individual method written by the programmer. Let's say the programmer picks, 3 different set of mutation operators to apply from the exhaustive listing. So when do we call these 3 mutation operators as being effective? Let's say the programmer, after testing with reference to these 3 mutation operators, also happened to realize that these 3 mutation operators also happen to kill other mutation operators that he didn't apply. Then you say that the 3 mutation operators chosen by the programmer is an effective set of mutation operators. So it will be a great thing if, per se, given a method or a piece of language, if you could have algorithms that determine right up front which are the effective set of mutation operators. Unfortunately, it's a difficult problem, an NP-complete or sometimes an undecidable problem, to be able to determine an effective set of mutation operators even at the level of an individual methods. But typically, various empirical studies in software engineering have indicated that mutation operators of this kind, those that insert unary operators and those that modify unary and binary operators, have proven to be very effective from the point of view of this definition. So that's the list that we are going to see in this lecture today. So what we do now is that I'll provide a list of program level mutation operators. What do they deal with? They deal with unary, binary, both relational and arithmetic and logical operators. They cut across several different programming languages. They can be applied for C, for Java, or for any other programming language that has a similar set. And I'll be giving you an exhaustive list of mutation operators. There'll be so many different ones. Please remember that you need not apply, given a piece of program or a method, you need not apply every kind of mutation operators. Choose a small subset from this such that you can make use of this list of mutation operators to be able to effectively mutate your program and test. It's useless to pick everything from this list because it's a fairly large list. So what are the exhaustive large list of mutation operators that at the program level that we are going to see? So that's what will the rest of the lecture be. So I'll give each of these collection of mutation operators that we are going to see a name like this. That name will be written in blue in every slide. So it just tells you what is the kind of mutation that we are going to apply. The first collection of mutation operator that we are going to see is what is called absolute value insertion. We'll see what it is. Later I'll tell you a set of mutation operators called arithmetic operator replacement. We'll after that do relational operator replacement. After that do conditional operator replacement. After that do shift operator replacement, and so on. We'll see a fairly large list. So each slide will have one collection of mutation operators that belong to one particular category. And remember, typically when you test your program, only a small number from this exhaustive set is enough to test your program. So we begin with our first set, which we call absolute value insertion. So what do we do here? Let's take a statement. If you look at this example here down in the slide, let's take a statement like x is equal to 3 star a. It's a normal assignment statement. What I'm going to do is that I'm going to change this to replace the variable a with its absolute value, call it as abs of a. I'm going to replace the variable a with the negation of its absolute value. This is called neg abs of a, and I'm going to replace a with 0 through the mutation operator fail on 0. So for this statement, which looks like this, a is an absolute value, that a is a variable for which I'm mutating by considering 3 possible different mutation operators. Instead of a, I take the absolute value of a. That's this first mutated statement that I get. The second one, instead of a, I take the negation of the absolute value of a. That's the second mutated statement. The third one, instead of a, I do fail on 0 of a, which makes a 0. So those are the 3 mutation operators. So this I can do for any statement given any program. So I say whenever I find an arithmetic expression or a sub-expression and I find a variable in that arithmetic sub-expression, then I can apply 3 different possible mutations to that variable. One possible mutation returns the absolute value of that expression or the variable. One possible mutation returns the negation of the absolute value of the expression or variable. The third possible mutation tests whether the value of the expression is 0 or not. If it has happened to be 0, then we say that the mutant fail on 0 is killed. Otherwise, the mutant is not killed, the execution continues, and the value of the expression as it was originally in the program is returned. So the next set of mutation operators that we are going to consider belong to this category of operators called arithmetic operator replacement. If you see in a typical programming language, what are the arithmetic operators that are there? There is addition, plus, subtraction, minus, multiplication, star, division, exponent, mod. So this is a reasonably exhaustive list of possible arithmetic operators. Now if you go down and look at the example, let's say there is a statement that looks like this: x is equal to a plus b. It has one arithmetic operator in it. This is the plus. So I could create 7 different mutations of this statement based on my need, where I replace this arithmetic operator plus with either minus or star or slash, which is division, or exponent, or there are 2 other special things where I knock off one of the operands. I retain only the left operand. Here I retain only the right operand, or I could replace this arithmetic operator with a mod. That's what it says. It says take any statement which has an arithmetic operator. In that statement, each occurrence. So this example, the arithmetic operator that we begin with is plus. But it could be the case that the original statement was x is equal to a minus b. In which case you choose something else in this list of arithmetic operators to mutate it with. I hope that's clear. So what it says is that the statement or the expression could have any of these arithmetic operators. You take that arithmetic operator out, replace it with some other arithmetic operator from this list based on your need. 2 special kind of other mutations can also be done. One mutation is called left op. What does it do? It returns only the left operand. The right operand is ignored. That's what we did here for this example. If I had a statement x is equal to a plus b, if I apply the mutation left op, it results in this: x is equal to a. That's a change that I make to the statement to see what would the program do. Similarly, right op returns just the right operand. So if I had the left one is ignored. So if I had x is equal to a plus b and I apply right op, then I get x is equal to just b. A is ignored. And what does mod do? Mod computes the remainder when the left op is divided by the right op. The standard thing. So is that clear? So in summary, what we're saying, there could be statements in the program which have arithmetic operations in them. One possible way to mutate such statements would be to replace that arithmetic operator that you find in that expression in that statement. If it is a plus, you could replace it with minus, star, slash, mod, and so on. If it's a minus, you could replace it with plus, star, slash, mod, and so on. So this collection of mutation operators put together is called arithmetic operator replacement. Moving on, just as arithmetic operators, you could do relational operator replacement. Again, what are the exhaustive list of relational operators that are available in programming languages? There's less than, there's greater than, less than or equal to, greater than or equal to, and not equal to. Let's say there was an expression that looked like this. I had an expression which says m is greater than n. I had a predicate, which says m is greater than n. My goal, maybe I don't know, maybe the programmer should have written m greater than or equal to n. So I want to mimic and see, is this a mistake made by the program? So I mutate the predicate m greater than n by replacing the relational operator greater than with greater than or equal to. So, or maybe sometimes the programmer intended to do less than, so I could mutate the predicate if m greater than n by replacing this relational operator greater than with the relational operator less than. So what it says is that any occurrence, each possible occurrence of one of the relational operators, which is this list, 6 of them, could be replaced by each of the other relational operator. In addition, you could do 2 special mutation operations. One is called false op, one is called true op. What does false op do? False op will replace this whole predicate with false. True op will replace this whole predicate with true. For example, if I had an if statement that looked like this, if m is greater than n, then I could create 7 different mutations from that. I could replace this greater than relational operator with greater than or equal to create this statement if m greater than or equal to n. Or I could replace greater than with less than to create this statement, greater than with less than or equal to, greater than with equal to, greater than with not equal to, this should be not equal to, then greater than with just false, maybe it is a contradiction, so it's useful to test it for this, and greater than m greater than n with just true. It tests for it being a tautology. So is that clear, please? So what are we saying? We say that if I have a predicate, a logical containing a relational operator, I could create a mutant of that predicate or a clause by replacing the actual relation in the relational operator by any of the other ones that are available. 2 special ones, I could replace the whole clause by true, I could replace the whole clause by false. Moving on, similarly, I can do conditional or logical operator replacement. So what does conditional or logical operator replacement do? What are the various logical operators? They are AND, they are OR, and with no conditional evaluation denoted by a single ampersand, and OR with no conditional evaluation which is denoted by a single vertical bar, and not equal to, which I denote by this caret symbol. So I could replace each of these with the other to create so many different mutants. In addition, I also have 4 special mutation operators. What are the special mutation operators? True and false, which are very similar to this one that we saw here. False returns false, true returns true. And I have left op and right op, which were similar to the ones that we saw in the arithmetic expression here, right op and left op. So true returns true, op returns true, false op returns false, left op returns the left operand, the right operand is ignored. Right op returns the right operand and the left operand is ignored. So for example, if I had a predicate that looked like this and an if statement with that predicate, let's say if A and B, then I could mutate the predicate by replacing this relational operator AND with any of the other ones. So I could replace AND with an OR to get this. I could replace AND with an AND with no conditional evaluation to get the second expression here. I could replace this AND with an OR with no conditional evaluation to get the third one. This is replacing AND with not equivalent. This is the fourth one. This is replacing AND with false. This is replacing A and B with true. This is knocking off the B from A. This is knocking off the A from A and B. I hope this is clear, right? It's a fairly routine thing. I take one operator of one kind, I can substitute it with any other operator of any other kind. Now you might ask, why can't I replace this AND with with let's say plus? That won't make sense, right? Why? Because the type of A and B is meant to be Boolean, and I should replace one operator with another operator of the same category. Please remember that the mutants that I create from programs still have to be valid in the sense that the resulting program has to compile. So arithmetic operators that we saw here can be replaced with other arithmetic operators only. Conditional operators, relational operators can be replaced with other relational operators only. Conditional operators can be replaced with conditional operators only, and so on for all the other groups that we are going to see for the remaining part of this lecture also. So the next set of mutation that you could do is regarding the shift operators. You might have seen these left shift, right shift, and right shift has two categories, signed and unsigned. So this is the left shift operator, this is the signed right shift operator, this is the unsigned right shift operator. Unsigned right shift is the counterpart of left shift. Signed right shift is meant to take care of negative numbers also. So each occurrence of these shift operators can be replaced by the other occurrence. In addition, I have the special mutation operator which just returns the left operand which is unshifted. So if I had a statement like this which says x is equal to m left shift a, I can mutate this statement to create three different mutations. I can replace this left shift with unsigned signed right shift. I can replace this left shift with unsigned right shift, or I can replace this left shift by knocking off the left shift and the a, don't shift, and return only m. So these are three mutations that are possible when you have statements in your program that deal with shift operations. Moving on, suppose you had statements in your program that deal with bitwise logical operators. That is, they work a lot like AND and OR, but when given a sequence of bits or binary numbers, they AND and OR or exclusive or bit by applying the same truth table for AND and OR. So each occurrence of each of the bitwise operators, the bitwise AND, the bitwise or the bitwise exclusive OR, can be replaced by each of the other operators when we do mutation operators here. In addition, I can also do left op and right op, like I did for arithmetic and other categories. Left op always returns the left operand, right one is ignored. Right op returns the right operand, left one is ignored. So suppose I had a statement like this, x is equal to m bitwise and n, then I can create three possible mutants of these statements. I could replace this bitwise and by bitwise or, this is the first mutant. I could replace this bitwise and by bitwise exclusive or, the second mutation. I could knock off the second left, the right operand and consider only x is equal to m. I could knock off the left operand and consider only x is equal to n. So these kind of mutations are possible dealing with bitwise operations. Similarly, I could also consider these assignment operators, plus equal to, minus equal to, star equal to, slash equal to, percentile equal to, and so on. And I could replace each occurrence of each kind of assignment operator with the other occurrence. For example, if I had a statement which said x plus is equal to 3, I can mutate it to create 10 different statements. I could say x minus equal to 3, x star equal to 3, x slash equal to 3, x plus mod equal to 3, and so on and so forth. Now, the other kind of mutation that I can do is unary operator insertion. What do we mean by that? Let's begin by understanding the example. Suppose there is a statement which says x is equal to 3 into a. Now, I can replace this a with plus a, create one mutation. This mutation turns out to be equivalent to this, because if a is positive, then plus a has the same sign as a. If a is negative also, then the same thing. So I list this for the sake of completeness, but these two are equivalent. Then I could replace this a with minus a, create another mutation. Similarly, I could replace 3 with plus 3. Here again, it's just an equivalent mutant. Might as well not create it because it gives the same expression, but it's listed here for the sake of being exhaustive. I could replace this 3 with a minus 3 to create such an expression. So that class of mutation operators is what is called unary operator insertion. What do I do here? Each unary operator, which is the arithmetic plus, the arithmetic minus, the conditional, and the logical, is inserted before each expression of the correct type. Here I had arithmetic expression, so I am considering only the arithmetic unary operators. Later I could consider the logical or the conditional unary operators. Just as replacing, I could delete a unary operator altogether. Each unary operator can be deleted. It could be the plus, it could be the minus, it could be a conditional operator, it could be a logical negation. I can delete it. For example, here I say if a is greater than minus b, I could say a is greater than minus b, which is the same as this, or I could remove the minus b and say a is greater than b. So I could remove that. Now, this is a very useful thing which we also used in the example that we saw in the last section. There are variables that I find in expressions throughout my piece of program, and those variables are called scalar variables because they're not as vectors. There's one individual variable. What I can do is I can mutate the program by considering each variable reference and replace it with some other variable reference such that the type matches, so that the expression continues to get evaluated. And not only the type should match, the other variable reference that I replace this with should be within the scope. That's what is true. This thing, I can't pick up another variable far away somewhere else in the program and suddenly substitute it here. It should be within the scope, because if it's within the scope, then things like declaring the variable and all other things will be taken care of. And mutating this way is effective than replacing it with a random undeclared variable. So for example, if I had a statement x is equal to a star b, then what can I do? I can take this and replace this b with a to create an expression like this, x is equal to a star a. I could replace the x with a to create another expression like this. I could replace the a with x to create this third expression. I could replace b with x to create the fourth expression. I could replace a with b to create this expression, and finally I retain the same thing. Is that clear? There's no point now in picking up a completely new variable, let's say c, that's out of the scope of this statement and replace x is equal to c into b. Maybe the program will complain saying c has not been declared and so on. So you don't want to risk. Remember, programs have to compile, they have to be valid. So when I do a variable replacement, I always replace variables such that the type of the variables match and the variable that is declared is within the current scope. Finally, we saw this last time. There's the special mutation available called bomb statement. What does this bomb statement do? Bomb signals a failure as soon as it's reached. It's like making the program fail at that statement and see what happens. This is another common testing heuristics which many companies that recommend unit testers to do. So they say reach each statement. So one way to make sure that the program execution has reached a particular statement is to replace that statement with a bomb. When the program reaches that statement, it will terminate, so you know that the program has reached that statement. So bomb is a very useful mutation operator. So what did we do in this lecture? We saw an exhaustive list. Please remember, the word is exhaustive. There's no point in considering each and every mutation operator that we saw today for every program that you test for. You should carefully select from this list which is the one that I want to test in my program, which is the property, which is the statement. If I want to test this statement for one particular property, which would be a good mutation operator to pick from the list that we learned today. That's how you should use it. And typically it's applied during unit testing to mimic typical programmer mistakes, as I told you. In the next lecture, what I'll be telling you is we saw mutation testing, and one question that might naturally arise in your mind is how does mutation testing compare to graph testing, or how does it compare to logical predicate testing, because they were also white box testing techniques, right? So that's what we will see. We'll see that mutation testing in fact is very powerful. It subsumes a lot of criteria from graph based testing and from logical based testing. Thank you.